Welcome to UBG Bytes, where we break down the latest in tech and security into bite-sized chunks. Today we're looking at something pretty fundamental to the future of AI, really. It's about how these smart agents, the ones popping up everywhere, are actually going to talk to each other and, well, the world around them. You've seen the explosion, right? AI agents powered by large language models. They're being deployed all over in different industries, promising incredible automation.
Absolutely. And we're seeing them move beyond, simple tasks. Now they're coordinating complex workflows, pulling in real-time data, interacting with legacy systems even.
Yeah.
They're becoming, well, digital actors in their own right.
But here's the big immediate challenge. It's a massive one. As these agents multiply, there's just no common language, no standard handshake for them to communicate effectively. Not with external tools, not with data sources, not even with other agents. It feels like building the early internet without TCP/IP or HTTP. Just chaos and fragmentation.
Precisely. That lack of standardization is a huge hurdle right now. It really limits interoperability. I mean, think about it.
Yeah.
An agent from one vendor can't easily use a tool built for another or collaborate smoothly with an agent developed somewhere else.
Yeah, that just kills scalability, right?
Totally. It hinders scalability, and it stops agents from tackling those really complex, real-world tasks, the ones that need coordinated action, information sharing across different systems.
And that's exactly where agent protocols come in. These are meant to be the essential standard frameworks. They provide the structured rules, the formats, the procedures, basically the grammar for agent communication.
They're designed to be the foundational plumbing, if you like,
Yeah.
enabling that interoperability and unlocking the potential for, well, truly collaborative and scalable agent ecosystems.
Okay, so the source material we're drawing from for this bite is a pretty comprehensive survey. It analyzes this emerging landscape of agent protocols.
Yeah, it does a good job mapping out what exists and, how they're trying to solve this communication problem.
So our mission for the next few minutes is to unpack what these protocols are, how they're being classified, maybe look at some key examples to see how they really differ. And then this is crucial for you, our listener, connect all of this back to security. What are the implications? What new attack surfaces are popping up? How does protocol design affect our defenses? Let's get into it.
Sounds good. At its core, this whole push for standardized agent protocols, it's about moving away from just ad hoc, custom integrations towards structured, reliable communication. And this is needed not just for agents talking to external things like APIs or databases, but increasingly for agents talking to other agents to build more complex systems.
Right. And how do these agent protocols really improve on the ways we used to connect systems? Just using standard APIs or maybe XML?
Well, they're built specifically for the agent paradigm. That's the key difference. APIs are great for straightforward machine-to-machine calls, sure, but they often lack the operational flexibility, the dynamism, the kind of standardized semantics that agents need to, say, negotiate tasks or exchange complex context. GUIs, they're obviously user-centric, not agent-centric.
Yeah.
XML was more about document exchange, structure. Agent protocols are really designed for efficiency in these AI-native operations. They have a wider scope discovery, negotiation, coordination, reliable state exchange, all with standardization built in from the ground up.
Purpose-built, then.
Exactly. For the complexity and autonomy of how agents interact.
That makes a lot of sense. They're optimized for this new world. Now, the source material, it offers a systematic way to categorize these protocols, uses a two-dimensional classification. Can you walk us through that?
Certainly. The survey uses two main dimensions to classify the protocols they looked at. The first one is object orientation. This basically looks at what the agent is primarily talking to.
Okay.
So you have context-oriented protocols. These are focused on agents interacting with external resources that are not other agents.
Yeah.
Things like tools, databases, web services. The agent needs context or needs to trigger actions via these things.
Agent talks to a thing.
Right. And then you have interagent protocols.
Yeah.
This category is specifically about agents communicating with each other, collaborating on tasks, exchanging information, sharing state.
Agent talks to another agent. Okay, simple enough. What's the second dimension?
The second dimension is the application scenario. Here you have general-purpose protocols. These aim to provide a broad framework usable across lots of different domains and types of agents.
Flexible?
And then domain-specific protocols. These are tailored more for particular use cases or industries, maybe human-agent interaction or robotics or specific business processes.
Got it. That classification helps put some order on this emerging landscape. Let's look at some examples then. Starting with the key one the source highlights. MCP, Anthropic's Model Context Protocol. That's general purpose, context-oriented, right? Agent talking to things.
Yes, MCP is a prominent example there. Its main goal is to standardize how LLM agents get external information and use tools, to gather context for their responses or decide what actions to take. Before MCP, it was, well, every LLM provider, every tool developer, they had their own proprietary way of doing this. It led to a really fractured ecosystem.
Right, so trying to get an agent from provider A to use a tool from provider B was a custom engineering job every single time. Painful.
Exactly. So MCP tries to solve that with a unified interface for accessing tools and data. A really critical architectural feature is its client-server model. It significantly decouples the LLM's abstract request, like, I need the weather, from the actual execution of calling the weather API.
How does that work?
Well, the LLM might say, I need the current weather for New York,
Mm-hmm.
but a local client component actually handles the API call.
Hmm.
And that client handles things like authentication, maybe data sanitization, before feeding the result back to the LLM.
The local client handles the sensitive parts, like auth. That sounds like a big plus for security.
It is. It's a major advantage for security and privacy. Because sensitive details, think API keys, user credentials, they stay local to the client environment. They aren't necessarily generated or handled directly by the potentially less secure LLM layer or sent over the network in a way the LLM directly orchestrated. MCP standardizes the request format from the LLM to the client, but the client does the heavy lifting securely.
Okay, so MCC focused on a single agent talking securely to external things, external resources. Now let's pivot to the other category, inter-agent protocols. This is where agents talk to each other. The source uses a great example here to show the differences. Planning a 5-day trip from Beijing to New York. That involves flights, hotels, activities, maybe checking weather, local events. Sounds like a perfect job for agent collaboration.
Yeah, the use case is really helpful for visualizing the different architectural patterns these protocols enable. So how would MCP handle that task, even though it's mainly context-oriented?
Well, in the MCP world, like we just described, you'd probably have one main travel planner agent, a central orchestrator. This single agent would be responsible for coordinating everything. It would make direct calls out to external tools or services. The flight API, the hotel booking service, the weather API, the calendar, requesting context or performing actions.
Okay.
The intelligence, the coordination logic, it's all centralized in that one planner agent.
Right. So all those external services are just treated as passive tools that the central agent knows how to use. The communication flow is like a star topology, isn't it? The planner talks out to each service individually.
Exactly.
It's simple to understand, maybe, but that central agent becomes a single point of failure, a potential bottleneck.
Right.
And it needs to know about all the different tools it might need.
So centralized intelligence with MCP, how does Google's A2A, the agent-to-agent protocol, approach the same trip planning task? This one is designed for agents talking to each other, right?
Correct. A2A is built specifically for complex collaboration between specialized agents, usually within a defined system or an enterprise boundary. So instead of one central agent doing everything, you distribute the intelligence. You might have a specialized flight agent, a hotel agent, an activities agent, maybe a weather agent.
Okay, different specialists.
And the main travel planner agent acts more like an orchestrator, or maybe just gathers the final results.
And do these specialized agents only talk back to the main planner? Or can they talk amongst themselves?
No, and this is a key difference from how you'd likely structure it with MCP in this scenario. The specialized agents using A2A can talk directly to each other if needed. For instance, the flight agent might need weather info. It could consult the weather agent directly about potential delays or optimal routing based on forecasts. That request doesn't necessarily have to route back through the main travel planner every time.
Ah, I see. So less central mediation for every little interaction. The communication paths are more flexible, more distributed, peer-to-peer almost?
Yes, exactly. A2A enables that more dynamic collaboration, and it uses established web standards, things like HTTPS, JSON RPC for efficient messaging, server-sent events, SSE for streaming updates. It seems designed with enterprise needs in mind, like security, privacy, traceability built in.
That sounds more robust for complex internal tasks within a company, maybe. Now, the Agent Network Protocol, AMP, that takes this collaboration idea even further. With its agent internet vision, how does ANP handle the trip planning?
ANP is designed for standardized cross-domain interactions. Think agents collaborating across different organizations, different administrative domains, potentially on the open internet.
Okay, wow.
So in the trip planning scenario using AMP, the flight agent might actually be run by an airline company, the hotel agent by a hotel chain, the weather agent by a meteorological service, all in completely different organizations.
So how do these agents running potentially on totally different infrastructure managed by different entities, how do they even establish communication and trust using A&P? That sounds challenging.
It is challenging. ANP aims to formalize these interactions with structured, protocol-based messaging specifically designed for independent agents collaborating. It relies on standards like JSON-LD for expressing data semantics clearly, and decentralized identifiers, DDs, for agent identity and verification across boundaries. So while A2A facilitates direct talk within a trusted system, ANP provides the framework for this kind of interaction across disparate, potentially untrusted boundaries. The ANP travel planner might orchestrate the overall goal, but the agents themselves negotiate the details using these formal ANP protocols. It's tackling that complexity of collaboration in a truly decentralized network.
Okay, that's a clear progression. MCP, one agent talking to tools. A2A, multiple agents talking directly within a system. ANP, multiple agents talking directly and formally across different systems or organizations. Now, what about Agora? That was described as a meta protocol. How does its approach differ in the trip planning context?
Agora has a unique flow. It's heavily focused on translating natural language user input into structured protocol interactions. It kind of sits as an intermediary layer. So when a user says, plan me a 5-day trip to New York, Agora's different layers work to understand that request, then translate it into the specific formalized protocol messages needed by the flight agent, the hotel agent, the activities agent, the weather agent, and then it distributes those requests.
Interesting. So Agora basically handles the messy initial natural language input and turns it into clean, structured commands that other, maybe simpler agents can easily process.
Exactly. It effectively shields those specialized agents from needing sophisticated NLP capabilities themselves. They just need to understand the standardized protocols that Agora generates for them. This allows them to focus purely on their domain expertise, booking flights, finding hotels, whatever. It's almost like a universal translator sitting at the input layer. Makes it easier to bring diverse agents into a workflow that starts with a simple user request.
And how does it communicate?
The source mentions it uses structured protocols for frequent interactions, but can fall back to less efficient methods if needed, so it tries to balance flexibility and efficiency.
That comparison using the trip planning case really does highlight the different architectural choices. It really seems like the choice of protocol depends heavily on what you need, doesn't it?
Absolutely.
Like, do you just need single agent tool use or complex enterprise internal collaboration or that ambitious cross-domain agent interaction? Or maybe you really need a strong natural language front end.
That's precisely what the source concludes. Their analysis in section 5.4 really shows that each protocol has a specific fit. It depends on the desired level of agent autonomy, how flexible communication paths need to be, the required level of interface standardization, and just the overall complexity of the task and the network of agents involved.
Makes sense. Now, beyond those core examples, MCP, A2A, ANP, Agora, the source, also mentions a few others, like ACONP, ACOMP, and Agent Protocol. Can we touch on those briefly?
Sure. The field is moving fast, so there are various efforts underway. ACONP, the Agent Connect protocol that's from Cisco and LangChain, is more of a standard interface for invoking and configuring agents, how you manage their lifecycle using APIs and descriptors.
Like starting and stopping them.
Yeah, that kind of thing. Then ACOMP from AI and Data IBM is apparently still in development, but aims to standardize practical agent communication features, focusing on automation and maybe UI integration. And the Agent Protocol by the AI Engineer Foundation provides a framework-agnostic standard using OpenAPI v3 mainly for control consoles to do basic lifecycle stuff. Start, stop, monitor an agent.
Okay, so lots of activity in this space. We've navigated the landscape, the classification, looked at key examples. Now let's bring this back home for our audience, the security professionals listening. Why should someone who's focused on finding vulns, designing secure architectures, or defending systems, why should they care about the nitty-gritty details of these different agent protocols?
Because these protocols fundamentally define the interaction patterns. They define the trust boundaries, the data flows in these future agent systems, different architectures, different communication methods. They introduce entirely new attack surfaces. They require you to rethink your security models completely. The protocol isn't just incidental plumbing. It's the very foundation upon which security has to be built.
Okay, let's make that concrete. Let's look at some of the evaluation dimensions the source uses in Section 4 and connect them directly to security concerns. First, the obvious one, security itself, Section 4.3. What should we be looking for in protocols from a security perspective?
Well, several key dimensions jump out. Authentication mode diversity is one. How robust are the mechanisms for verifying identity? between agents, or between agents and tools. If there's only one weak method, well, that's a clear target. Role or ACL granularity is also absolutely critical in multi-agent systems. Can we define very fine-grained permissions? What exactly is each agent allowed to do or access?
Yeah, least privilege for agents.
Exactly. If a low-privilege agent gets popped, granular controls are what stop it from moving laterally, or accessing sensitive data, or functions it shouldn't. Without that, one compromised agent could potentially cause chaos across the whole network. Also, context desensitization mechanisms are vital for privacy, preventing data leakage. How is sensitive data handled during communication? Is it automatically masked, tokenized, restricted based on the agent's privileges?
How do different protocols handle that?
They vary. We mentioned MCP with its local client handling auth. Others like LMOS, which wasn't one of our core examples but is in the source, might use things like W3C DIDs and OAuth2 in their identity security layer, different approaches.
So security isn't just a single feature, it's about the depth and breadth of the controls the protocol actually enables. What about reliability? That's section 4.4 in the source. How does ensuring messages get through reliably relate to security?
It might seem like just performance or correctness, but reliability metrics, things like packet retransmission, flow control, persistent connections, they have serious security implications. If communication is unreliable, think about what an attacker could do. They could exploit that to inject malicious messages, maybe drop critical packets to cause incorrect state or decisions, or even cause congestion leading to denial of service.
Or cause errors that leak information?
Potentially, yes.
Yeah.
Unreliable delivery can lead to race conditions, state confusion in the agents, system failures, all of which might inadvertently expose data during error handling or recovery. Metrics the source mentions like automatic retry count ARC, convergence time CT, and message loss rate MLR become relevant security indicators too.
Okay, and scalability, section 4.2. As these agent networks grow from maybe dozens to potentially millions, what security issues pop up then?
Scalability looks at how well the protocol handles more agents, more connections. Metrics like throughput per second per node, TPSN, and capability negotiation score, CNS, are important. A protocol that doesn't scale gracefully, it can suffer performance issues under load, right? Which might make it vulnerable to DOS attacks. Or it could introduce subtle race conditions and timing vulnerabilities when things get really busy. Plus, just managing authentication and authorization for a massive, dynamic network of agents? That's a huge security challenge in itself. The protocol design needs to support that scaling securely.
And interoperability, section 4.7. That sounds like a good thing, essential even, but maybe also a risk.
It is definitely a double-edged sword. Interoperability measured by things like schema compatibility test pass rate, SCTPR, is vital. It allows diverse agents and tools to work together. That could include security monitoring agents or incident response agents, which is good. However, if a fundamental vulnerability is found in the protocol itself, its widespread adoption means that single vulnerability could affect a vast ecosystem of systems all relying on it.
Like discovering a flaw in HTTP or TCP/IP today.
Exactly. It becomes a potentially universal attack vector. The standardization that enables interoperability also concentrates risk if the standard itself is flawed.
What about adaptability or extensibility? Section 4.5. These protocols aren't static. They'll need to evolve, right?
Absolutely. And how they handle evolution is key for security, too. Things like backward compatibility, flexibility, customization support. A protocol that isn't designed for graceful extensibility. Well, you might introduce security flaws when new features get shoehorned in later. Or you might end up with scenarios where older, insecure versions stick around because upgrading is too hard or breaks things.
Okay, so for us security professionals, assessing these agent protocols, it goes way beyond just looking at the features explicitly labeled security. We need a broader view. We need to consider security itself, obviously, but also adaptability, reliability, and interoperability. Maybe we can use SARI as a shorthand, a way to remember these crucial evaluation dimensions when we're analyzing the security posture of systems built on these protocols.
SARI. Security, adaptability, reliability, interoperability. I like it. It provides a practical framework for thinking about the security implications that are woven into the core design of these protocols, not just bolted on afterwards.
So looking ahead, the source paints a picture of the future in Section 6. What are the short, mid, and long-term trends they see for these agent protocols?
In the short term, expect a big focus on developing unified evaluation benchmarks. We need better ways to compare protocols rigorously. Also, creating more privacy-preserving protocols, ways agents can share aggregated insights, maybe rather than raw, sensitive data, and exploring agent mesh protocols. Think of it like standardized ways for groups of agents to interact collaboratively, almost like a structured group chat for agents. Protocols are also likely becoming more evolvable, able to adapt their rules dynamically to some extent.
Okay. And midterm, what's further out?
Midterm trends. We might see protocol knowledge being increasingly built directly into the LLMs themselves. So agents could natively understand and adhere to complex interaction protocols without needing explicit detailed prompting every time. We might also see more layered protocol architectures emerge, separating concerns like how messages are transported from the higher level semantics of the agent conversation, similar to how the internet stack works, TCP, IP, HTTP, etc.
Makes sense. And the really long-term vision.
The long-term outlook gets pretty fascinating. It includes the potential emergence of genuine collective intelligence as vast networks of agents interconnect and coordinate in complex ways. And perhaps the most ambitious vision mentioned is a dedicated agent data network, an ADN.
An agent data network, you mean like a separate internet just for agents?
In a way, yeah. It's envisioned as a foundational network layer, maybe sitting atop the existing internet stack, but specifically optimized for machine-to-machine exchange. It would focus on the efficient, structured, persistent exchange of things agents need for long-term collaboration, stuff like latent task states, distributed memory components, temporal context logs, data that's crucial for agents but doesn't necessarily need human-readable formats.
Wow, that sounds like a pretty dramatic shift in network architecture if it happens. And as agents do become more interconnected via these protocols, maybe moving towards something like that agent internet vision we talked about with ANP or LMS, this leads us right to the provocative question for you, the listener, to ponder.
As these complex, decentralized, collaborative intelligence networks start to emerge, all enabled by these evolving protocols, how fundamentally will our security testing methods, our defensive strategies, how will they need to adapt? What completely new attack vectors will arise when the systems we're trying to secure are actually composed of these autonomous, communicating learning agents?
Yeah, think about that convergence the source mentions between context-oriented protocols and interagent protocols. What happens when the tools an agent uses are themselves other agents? And agents acting as collaborators can also initiate tasks and use other agents as tools. What happens when tools are agents and agents are tools, all talking to each other through these complex, evolving protocols? That's the landscape we seem to be heading into. And securing it, well, that's the challenge.
It definitely requires a shift in mindset, moving from securing relatively static systems to securing these incredibly dynamic collaborative ecosystems.
That's all for this bite of InfoSec Insight. Until next time, stay sharp, stay curious, and keep breaking things responsibly, of course.